Hello everyone. So welcome back to the next class on this course on net zero emissions through the energy direction. So what we were looking when we met last time was we looked at energy efficiency as the one of the measures in reducing the overall energy need. So energy need is what we were trying to work upon, that how energy need can be reduced by using energy efficiency as a measure. And if we can reduce the need, then it will in turn would mean lesser generation. It means lesser money needed for creating those generation devices, and that would also would mean in terms of making a cheaper transition, because what we also discuss is that once you save the energy, that's in a way the cheapest way of generating a unit, because that is almost no cost or very minimal cost through which you can do it. Let us look at one more aspect of this energy efficiency, which is coming on from the demand side management. So what do I mean by demand side management? Let us first try to understand that why demand side management is even important, that why are we talking about demand in particular. Try to understand that energy we produce only when there is a need to use the energy. So energy is not governed by the generation. Energy is always governed by demand. So there is a demand which is there, and you are trying to fulfill that demand, and to fulfill that demand you are trying to generate, not the other way around, that it is you are generating just because you are generating and then you consume it. It's just the other way around. You have a demand, and that demand is doing some generation around it, right? So what we have talked about, the energy efficiency focus on using less energy for same service. So effectively what we are saying is that for same service we need less energy. So for the same demand, because that is the work that we are doing, for doing the same work, when we have a demand, we are doing some work in the background. So doing the same work, we are needing lesser energy. That's what the energy efficiency was all about, right? But what we are missing in this equation is that this demand may actually vary over a period of time. This demand may not be constant. We'll look into these examples more and more, but if you then start looking at more seriously, suppose you have a vehicle, suppose you have a car. You will have the maximum demand to get energy from that car would be in the morning and in the evening when you go to the office or when you come back from office, like, or over the weekends, maybe when you're going for your family trips. It will be very uncommon to have a constant demand for a car or a vehicle to give same kind of energy throughout the day. So there is always a time dependence on this demand. There is always a time dependence on when do we need this energy to be supplied to us in a most efficient way, so that we can utilize that rightfully. So in this section, what we look is for that how the energy efficiency measure is also extends to power system operations and planning. So it is all about planning. So it is not only about reducing the energy demand, it is not only about improving the efficiency of overall system, but what we also need to see is that are we doing it at the right time? Are we making it the most effective way it could be done? So demand side management, it kind of connects this end user behavior with the system level design aspects or system level outputs is what we will be looking into. Like why we are talking about it now, because see what we have looked into is that we have looked into that energy efficiency reduces energy intensity at the device and process level. What we need to now understand is that once we have understood that this can be done, what we need to see is that it is not only how much energy is used, but it is also important for us to understand is when it is to be used. And since we now need to now understand that, that's why we are now coming to this section where we are now trying to understand that when do we need this energy to be used. And because sometimes a system, as I talked to you in the morning, and if you do a kind of a time versus energy need graph for the vehicle that I just talked to you about, then if you start plotting it around, for suppose 12 o'clock one midnight to 12 o'clock another midnight. So the night the car is in your garage. So almost, if this is a zero level, so almost your car will not be functioning. Then in morning there would be suddenly peak around it. Then in the daytime you may have then the sunlight will go down. Then daytime you may have some meetings or some other meeting, and evening then you will need to come back. Now, there's a huge time dependence around this whole thing. So now this time dependence would also mean in terms of that there will be a large variation around within a day. There is a huge variation in terms of when do we need this energy. So if we are putting some energy efficiency measures, we need to be wary of the fact that when do we need this energy. And Then there could be some seasonal fluctuations around it. Like for example, if I am using some cooling at my home, and when do I need to use the energy? Like so suppose in the night, again let me plot it from 12 to 12. In the night, I may be using AC at a certain power, but in the morning, when I go to office, this AC need kind of goes down. Both my family members have gone for office. In evening, when we come back, again this AC needs to be at the peak because the house have kind of heated up in the daytime, and then by certain time when I finish my dinner, when I'm trying to go to bed, this I may reduce the use of AC to certain different temperature. So there's always a time dependence on the kind of power during my consumption pattern. And so this kind of a demand side management, how do I manage this demand, is kind of helps me to understand those kind of constraints that efficiency alone cannot solve, right? So why efficiency is not the only solution, because it reduces electricity at the point of consumption. However, it does not reduce automatically the peak demand. As I talked about that, I can have the efficiency measures coming in. What is efficiency doing? Efficiency is reducing overall the energy demand, but my peak can still remain the same, or peak can still remain very high. And what I'll show you in the coming slides, it is a peak factor which could determine that how effectively you are able to modify or reduce overall stress on your system. It also, they do not directly improve the grid stability, because again, okay, let me try to tell you this a different way. Okay, let it come on the next slide. But overall, what you need to understand is that it may not also lower the overall infrastructure needs also. So power system and cost, it depends upon the aggregated demand profile, not individual devices price. So I showed you one device performance, like I showed you this AC performance, which kind of went down like this. And I told you AC performance, the peak demand was coming. But is it only AC you're running at home? You're not, right? So it is not only AC that you're running at home. So if you do a time versus energy requirement, there'll be other devices at home. The other device may have a profile like this. Other device may have a profile like this. Now the overall energy requirement which you will have at home would be a kind of a convolution of both the demands put together. So suppose this is demand A which is running like this, the demand B is running like this. So overall the requirement for the demand would come as an addition of these two demands. So there will be a graph which could be looking like this. So while there was in the earlier graph, when you were only running AC, you had a situation where your power was not consumed in the daytime at all. Now you have a situation where your power is also being consumed in the daytime also. So it is the overall system cost will be determined by multiple factors. It will be determined by the overall load of all devices put together, and also it will be determined by what is the peak power, because you want a reliable system. And since you want a reliable system, so you always will have to design the system as per the peak power requirement. You cannot have a system which you can simply design based on the some average power which you can take. Suppose this was a graph, and suppose your average power which was there was, suppose this was the average power that you need. You cannot design the system at an average power, because if you design it your system at average power, there will be a power cut whenever the power kind of goes above the average power generation. So this will complicate the whole system designing in a very complicated way. And through energy efficiency measure, what I am doing is that I am reducing my energy demand overall. So my overall energy demand has kind of reduced, but have I reduced my peak? If I have not reduced my peak, the chances of a load cut or shade cut can even be higher. So this kind of complicates the situation in terms of that if I am not wary of the fact that my demand can vary during the period of the day and or with seasons, I need to be careful about that fact overall. So just to kind of reiterate this fact, electricity must be produced at the same time when it is consumed. See, otherwise my storage capacity will be huge. So if I am not using the electricity when I am producing it, I may be looking for to store the energy in big capacitors or big batteries or big other kind of storage devices. That will be a cost in itself. So the best way to reduce the system cost is that electricity should be produced when it is consumed, because large scale and low cost storage has historically been very limited. So one of the technology here which I'll show you later on is pumped hydro storage, which kind of works good in this sense. But overall, as you can imagine, whatever I do, there'll always be a round trip efficiency loss, like so generation to storage, storage to generation, or storage to point of use. So they, instead of direct generation to use, there'll always be two more transition which will happen, and because of these two specific transitions which are happening, there'll always be losses, and there'll be a overall cost which will increase the system. So what happens is that since my demand varies by hour, my demand varies day by day, my demand varies season by season. So this demand variation is kind of becomes central to any power system design, because we want to have a system where we generate and we supply and we consume. And since we want a system like this what would be an ideal system, and since my usage pattern changes over the period of day, so my generation system designing always depend upon my usage pattern, and that what makes this energy efficiency discussion, it takes energy efficiency discussion in a very different direction now, right? So the load curve, which is a curve which is of how much load is there during the period of day or any period of time that we are talking about, it kind of captures the daily routines which are there. It talks about some peaks which could be industry dependent peak. They could have some variation which could be weather dependent variations also, but it kind of provides a system level overview, and that's why as electrical engineers or as energy engineers, especially as energy engineers, for us to understand this load curve becomes key for system level designing. So during my research, when we work on this energy transition modeling, from taking this energy generation from current sources of energy to a new sources of energy, we always keep in mind in terms of that what is this load curve. So load curve kind of becomes our starting point for any system designing perspective. So that's where we kind of start with that. Even when we work on efficiencies, even when we work on alternative generation, we always start with the load curve, because that kind of tells us what is the right amount of energy that we need throughout the year. So usually if it is possible, we try to get a data point for every hour, and because for each hour the hourly pattern can change from month to month, day to day, and even at times we try to do this thing that we try to take multiple year averages if that is possible through some data, because that will kind of also avoid us some kind of a very local variations with respect to some specific event which might have happened for that year itself, and is there averaging effect over multiple years, because that's how the right system designing would take place. What does the load curve tells us? It tells us that what is the maximum demand that system should be able to serve, because we don't want any power cuts. So since we don't want any power cuts, so what we look for is that what are the maximum power that we need throughout the day, at any point of the day or any point of the month or any point of the year. Year would be the right term to talk about that. When do we need maximum power? Which period of the year? And then the next point that tells us that for a specific period, the area under the curve, if we just multiply time into energy, basically that will tell us that overall what is this overall electricity consumption multiplied. So because we will get a kilowatt hour kind of a situation, and then if you multiply this with time, we will get overall what is the total electricity consumption that we are getting, that we need to kind of produce. So area under the curve tells us the total amount of electricity that we need. Peak tells us that what is the maximum electricity or maximum energy that we need at a specific period of the day or a specific period of the year. And our load factor also defines that how efficiently my infrastructure is used, because then if I am generating my power at the same time as I am consuming it, then my system is very efficient, and if I am not using it rightly, then my system could be very inefficient, because if the two curves are not very overlapping a lot. And also what you need to understand is that two curves could have very similar areas but could have very different consumption patterns. Two systems with identical consumption, that the area under the curve is same, but their patterns could be very different. For example, one curve could look like having consumption pattern like this. Second curve has a more lower values, but the area under the curve in the two cases is same. Now, if the area under the two curve is same, what it would mean is that I will need to design this system for this maximum power, while in the other case I need to design system with a lesser overall peak power. So in terms of grid that I would need to design, grid as per this power in case A, and in case of case B, I need to design my grid only up to this peak power also. So same kind of a overall consumption could also would mean very different kind of a overall system design requirement. So this variation becomes very interesting for us to understand. And why does this peak demand dominates system cost is because, as I was telling you about, is that our generation, transmission and distribution have to be all designed around the peak power, because we require peak power to be met. We don't want average power to be met. And since we want peak power to be met, so all our system designing happens around it. And if we have system in which we have very high peak demands and we have overall lower consumption, so what we are talking about? We suppose our maximum power demand is 10 gigawatt hour, and my average power requirement for that system is about 2 gigawatt hour. Now, though the average power requirement is only 2 gigawatt hour energy requirement, but since my peak is at 10 gigawatt hour, so I will have to design all my infrastructure to supply for 10 gigawatt hour. So for most period of the day, or most period of the time, my overall system will be highly underutilized, because I have designed all my generation, all my transmission, everything around the highest energy demand which I can expect. Now, since the system would be done at the highest energy requirement, but since I am using the energy at a much lower average, so my system will be highly underutilized, and my return on investment on my infrastructure will be badly hit. So that would also mean, in terms of that, higher cost of electricity which I will be able to supply per unit, because of this underutilization of my assets. So overall, if we are talking about that from an overall system level perspective, if we start looking into that, if we design a system that efficiency can go low, that does not mean that I am designing that my peak can go very low also. So that would mean, in terms of that, that whole advantage of efficiency may go away, because I may not be able to reduce my system cost. The overall consumption cost may go down, but my system cost will remain high. So what can be done is, and what we'll see in the next few slides in terms of what specifically can be done around it, that what we can do is that, suppose I have a system in which it is peaking at a certain hour. Can I distribute this peak in a certain way that overall, since as I said, about 10 gigawatt hour is my overall my peak demand, and my overall average demand is at a 2 gigawatt hour. Can I reduce my peak by pushing some power, or pushing some need when my overall energy needs is lower, right? Because that in a way distributing the system in a right way, so that I can remove the concentrated uses power. Because then if I can do that, and if I can reduce this peak from say 10 to say suppose 4 gigawatt hour, so then I will need to design my system only for 4 gigawatt hour instead of designing it for 10 gigawatt hours. So that will overall reduce the system cost, and this will also help us to maintain the system in a much more efficient way also, because then my generation and my consumption can have better overlaps, because then I'll not be working with a system in which I have over designed the system, and since my system was over designed, it can only produce so much, or it can at max it can go at a certain level to not to produce, like, so even if a system which is designed at 10 gigawatt hour, for example, right, I cannot run that system at 1 gigawatt hour at few hours of the day, and at 10 gigawatt hours suddenly, because then there will be a huge ramp up which the system has to go. And if this ramp up is not possible through the technology, then what I may end up doing is that, though my requirement is only 1 gigawatt hour for that period of the day, I may have to run that system at 4 or 5 gigawatt hour, so that, one, because I don't want my generators to trip. Second, I may not be able to manage this fast ramp up. So since my ramp up can only be slow, so I will have to then work out a mechanism in terms of that, what is the minimum generation at which I need to continue to run my system, so that I should avoid tripping of the system. I should avoid that I am not able to meet the demand suddenly, because then if the sudden demand comes in, it should not that I should be lagging that demand, and then the system will again become unreliable or inefficient. And with the renewable energy coming in, and this demand problem is actually aggregating more. So till now we are talking about sources which can give power as per our requirement. So a coal plant or a gas plant or any plant which depends upon the sources which can be accumulated, stored, and can be utilized at a period of time, I can produce energy as per my requirement, barring a few things where my system needs to have minimum kind of a running to maintain the system efficiency, so the system doesn't trip and all those things. Because sometime when a system is designed at 10 gigawatt hour of production and you want to run it at 1 gigawatt hour of production, which is 1/10 of the generation that you're talking about, some systems are not able to have this kind of a dynamic range in terms of production. So some systems have this minimum requirement that you may need to produce 4 to 5 gigawatt hour for system stability, otherwise system will trip. To maintain that, we may have to do that. But having said it, but still I can run it, I can produce it, I can produce energy from it as per my need. I can always keep on producing energy from sources like coal or gas or oil. Since they are all dispatchable energy sources, I can dispatch them from one location to another location. I can store it and I can use it as per my need. Now the problem in renewables, which as soon as I start using my renewable energy sources, now renewable energy sources have their own temporal variation, they have their own seasonal variation, they have their own variations which are inherently present purely by the nature of those sources itself. So since it depends upon that, so the whole electricity demand curve now has to be looked into very different perspective, because then my whole system designing does not only depend upon that how much demand is varying, but now I have to worry about my generation variation also, and those two has to be now married or worked out efficiently in both ways. So this system gets much more complicated. This demand management things becomes much more complicated as soon as the renewable energy generation is coming into picture. So there is a classical curve around this, which for solar, what we talked about, that first time it was developed in California, that there is a curve called duck curve, in which what is happening is that, let me come to you here, that you have your energy requirement. Suppose the energy requirement is this, let's assume it is flat, right? But your solar generation is happening more during this period only. So since solar generation is happening only during a specific period, so there is no solar generation, or effectively no solar generation which is before 9 AM, and there is effectively no solar generation which is happening after 6 PM. So now if you look at the net demand, so suppose this partial demand, whenever you are able to produce solar, produce energy from solar, then you use solar energy, but your net demand, which is basically overall demand minus generation from solar. If you start doing that, then suddenly your net demand curve start taking a shape which is something like this. Because now what is happening is that during some period of the day, suddenly you have a period where you have higher generation than your demand at that time, or okay, let me not take that scenario, but your demand is primarily met by a source which is available at that period of time. So from a very flat system, now from a system which was looking very much more flattish in nature, if without this, suppose a system was looking, your demand curve was something like this earlier. Now in 2019 the demand curve was like this. So your demand had a valley here, a kind of peak here, it was kind of looking flattish. But as soon as this solar starts getting generated, now what you have suddenly a situation is that you have this valley coming in here, and as soon as this starts valley coming into picture, you have two more, you have a situation where you have peaks emerging at a different period of time. Now you need to design a system. Obviously the system design is at a lower power, because some of the power you are able to meet through solar, but suddenly you need to have a system which needs to have much more faster ramp up. You need to have a system which has much more sharper peak compared to peaks in the earlier system. Now so this kind of complicates the overall system designing from a design perspective overall. So this is a very interesting phenomena which people have started noticing when the renewable energy has come into picture, because with the renewable energy coming into picture, this we are not only talking about the demand side management also, but generation side management also, and from overall system design perspective, now this whole equation of demand and system demand and generation management complicates this equation much more than the earlier situation. So this phenomena is known as a duck curve, where the net energy demand kind of start taking shape of a duck, and the deeper is the value of the duck. So deeper it goes, the tougher is the problem of system designing, which kind of comes into picture. And why does it matter? Because as I already told you, is that it may require very rapid ramp up of flexible generation, because your ramp up suddenly, which was only this much, this kind of a ramp up, the slope was this much. Now, so look at this, compare the slope in the two cases. Your slope increases a lot. It may also lead to a situation where you may need to cut the renewable energy generation also, because you may not be able to design a system which can give you this kind of a peak power and goes as low as this to give you the power at when you have the solar at a maximum. Maybe the system can will get tripped if you go beyond this point. So you may have to generate power of this much of power throughout the day. At least minimum energy that you need to generate is this much. If minimum energy you need to generate is this much, then what can happen is that this excess generation of renewable energy, which is bound to happen during this period, you may have to cut it off. You may have to have a situation where you may not be able to generate this energy from renewable energy anymore during this period of the day, because you don't want your primary system, which is supplying you energy throughout the day for the rest of the day, you don't want that to get tripped. So you may have to have a situation where you need to cut on the renewable energy generation. It may also lead to a situation where electricity generation prices may have to be drastically cut during this period of time, especially from renewable energy, because you may have a situation where you want people to suddenly consume more, or you want a situation where you have excess generation and you have you cannot store electrons because you don't have that storage available with you. If you don't have that storage available with you, then you may have to sell electricity at a very cheap rate during this phase, just to avoid any tripping of the system from an excess generation perspective. So just to give an example, it happened in India also last year, because suddenly the demand from a couple of states went down drastically, and the renewable energy generation power was sold less than a rupees. I have heard that in some reports say that it was sold as cheap as 2 paisa per unit for a very short duration period of time. So that is a situation which can happen for any geography. So this also kind of gives a challenge to the economics of the conventional base load plant, because now you are talking about a base load plant which needs to either operate at a high efficiency or high generation at this period of time, and then it needs to generate at a very low generation point during some other period of the day. Now, where do you pay it? Like, do you pay it for the average generation? Do you pay it for the peak generation? And depending upon that, the whole economics of this energy generation system can be very challenging. So this kind of a demand variation, including the generation variation from renewable energy sources, makes this whole situation of this demand versus energy, demand versus generation equation very tight with respect to energy efficiency measures also. Because how do you define your energy efficiency in this case? How do you kind of work a situation where you, along with energy efficiency, now you are given with two complications on top of it. One complication I have talked to you is in terms of demand variation. Another complication I have talked to you is in terms of generation variation. So this transition which is happening, so along with, so one is demand side management, which was a challenge in itself, and we will look more into this situation more and more. But at the same time, we also have a situation where we have this generation side variation also. So this is making this whole transition of energy transition a very much more challenging task. And we will look into this more in the next class, and then we will look into that what is being done slightly on these lines to handle some of these situations. Thank you.